Hi everyone, my name's Owen Conhart, and today I'm going to talk about the effects of image distribution and task on adversarial robustness. And this is a project in collaboration with Dr. Ochoa and Professor Tommaso Poggio at the Massachusetts Institute of Technology. So what is an image distribution? Well, it's a way of characterizing properties of an image data set. For example, we may look at a color histogram, shape of the images, or perform a Fourier transform and look at the spectral properties of these images. And so the spectral properties of a digit, an object, a scene, and a texture. And these images appear different due to different spectral properties. So the goal of this project is to understand the role that image distribution plays in the adversarial robustness of a model, which is essentially a model's ability to resist images designed to cause the model to misclassify. And these images designed to cause the model to misclassify are called adversarial images, and often they look so similar to actual images that a human can't tell the difference, yet the model will still get it wrong. And this is widely cited as an example of the divergence between machine and human perception. And so adversarial robustness can be measured as the rate at which accuracy changes as epsilon, perturbation strength, or how much we change that adversarial image, increases. And so area under the curve of a function f of epsilon that outputs the adversarial accuracy, or how our model performs on these adversarial images for some given perturbation strength can be over some interval of perturbation strengths. But this has a limitation. And that is that models have different initial performance, so regular awk is a biased metric. And this is because some tasks are more discriminable than others. Take, for example, ResNet 50, trained on CFAR, scenes, texture, or MNIST. MNIST performs the best, but our differences in robustness by virtue because learning digits is easier than, say, objects, or is it actually more robust? And so one solution is to normalize with respect to initial performance, then take the awk. So, for example, here, it's hard to tell if one model is more robust than the other by virtue of their offset. But here, when it's normalized, we can clearly see that this blue model performs better. And this is, in terms of adversarial robustness, and this is with respect to where it started. And so here's the metric. This is the area under the curve. This normalizes by our initial performance, which again, we're now looking at with how much we're changing with respect to where we started. And then this normalizes with respect to our epsilon interval, which is essentially our interval of perturbation strengths, where epsilon naught is a lower bound and epsilon 1 is the upper bound. And so our metric is in this left half open interval, 0, 1, and we have this constraint of for all epsilon greater than or equal to epsilon naught, f of epsilon is less than or equal to f of epsilon naught. And essentially this constraint is saying that as our perturbation strengths increases, our accuracy decreases from where we started. So we want this constraint to be satisfied because otherwise we wouldn't be a good adversary. So experimental setup. We use 5 data sets, MNIST, which is digit, CFAR10, which is object, scenes data set, texture, and finally a fusion data set, which is an alpha blending of these MNIST and CFAR10 images. And we use this to tease apart the cause and effects of adversarial robustness in a model. And so here are more examples of these fusion images. And so essentially the data set is fixed, but the task varies by model. The architectures are shallow fully connected net, LaNet, ResNet 50. And our method is we train a model for each architecture in each dataset 20 times, reaching about state-of-the-art performance. And we attack each model using fast gradient sign method. And this is a method to generate adversarial images. And so here's how the procedure works. We have some base image, say from our test set, and then we carefully find noise that increases the loss. We scale that, usually so a human wouldn't notice a difference. We add that to a base image, and then that's how we get the adversarial image. And so we get the accuracy of models on these adversarial images, and from there compute the adversarial robustness. So now let's finally look at the these performance curves for these different models. And so here it is for fully connected net, for CFAR10, scenes, texture, and MNIST. And these are the normalized accuracies, so you can get kind of some of the intuition or a sense of what the metric, this adversarial robustness metric might be. It is for LaNet and ResNet 50, and we can see that MNIST models are clearly more robust. And so now let's figure out whether it's the image distribution or task that is causing this adversarial vulnerability or robustness. And so we're going to use our fusion data set and compare it to CFAR10 and MNIST. And so here's the plot for normalized accuracy. This is the FCNet, this is the LINET, and this is ResNet 50. Comparing CFAR10 and the fusion object, we can see that CFAR10 is more robust. Comparing MNIST and fusion digit, we can see that MNIST is more robust. Because the task is the same, but the image distribution is different, we know that the image distribution is contributing to robustness. And then we compare fusion digit and fusion object. We see that fusion digit is more robust, and because the data set's the same but the tasks are different, we know that task is also contributing to adversarial robustness. And so now let's actually compute the metric. Here's the adversarial robustness on those data sets for fully connected net, for LINET, and for ResNet 50. And we see that in general, MNIST models are the most robust. Scenes are generally the least robust, at least for natural image distributions. And we can actually see that architecture may also contribute to this from these plots. So we learned that MNIST models are the most adversarially robust and scenes are the least adversarially robust for the natural image distributions that we tested. Both the image distribution and task together or individually contribute to the adversarial robustness of a model. And understanding the role image distribution and task play may actually inform learned image representations in humans, which is why this is worth exploring for vision science more generally. So here's some related work. And for future work, we'd like to investigate what specific factors of task and image distribution impact adversarial robustness. Now, thank you for listening